Welcome you all. Continuation to our previous lecture videos. I think we have covered almost all the major concepts regarding your soil solids and soil water. So today we shall move on to soil air and soil aeration. We all know in today's time the major concern is our climate change. Have this climate change is happening because of air pollution, industrial activities, all these we know, but we will strictly stick to our main topic, which is soil air. So what is soil air? We already discussed several times that in a soil there are mainly three phases. One is your solid, liquid and gaseous phase, or we can say soil air. We see again a ideal loamy soil. I am drawing an ideal loamy soil. We already know that 50% will be pure. This is an ideal loamy soil. Ideal loamy soil. We already know there are three phases. One is your solid, one is your liquid, and another one is your gas, or we can say rather air. So we already studied different physical properties of soil. So think now of a compacted soil. We will see how the soil air changes. Simply do trigonometry. Okay. If you see a compacted soil, what happens in soil compaction? The ball density increases and this excludes most of the soil air, but does not change the soil water content. You already know all this, we have discussed. So in compacted soil, you can say now almost all soil volume are excluded. Soil air volume has been excluded. So this high percentage only now soil air remains. This is your water, 25%, and your solid, which is almost you can see 75%. This is in a compacted soil. You can clearly observe how the soil air status is changing. In another type of physical soil, you can observe also how this changes. There are many conditions where you can observe. To get acquainted, I am doing 2 to 3 figures so that you will be clearly understand how the soil air is changing. Now consider a saturated soil. What happens in saturation? All the air volume now will be filled up with water. So, if one component is your solid, already know, and your water almost covers 45%. 45% area is covered by water. And how much of air now remains? Only air is pure 5%. From here, this is a saturated soil. Saturated soil. Now you can clearly observe how the soil air is changing. So if we discuss some major or main factors which affect this air change, we can say one is your water. One is your water, as water, or sometimes we say in soil terms we can say moisture. Okay. If the moisture content is increasing, so what will happen? Very simple, the air will decrease. Or rather, we use the term aeration. What is aeration? Aeration is simply, we can say, gaseous exchange between your soil air and atmosphere. This we already know, all of us know. I think this is a very basic chapter, but we also need some scientific concepts to remember this chapter. And another major factor we can say is your biological activity, because all those flora, fauna, all those biological activities that prevail in your soil, that depends on the air. Along with water, this also depends on the air, because for respiration, all these activities, metabolic activities, they need the air, good quantity of air. Okay. So another important factor I can say is your biological properties or biological factors. If you think the activity of your flora fauna is more, so what will happen? They will respire, more carbon dioxide will be produced. So more carbon dioxide will be produced. No? Instead of oxygen, the more carbon dioxide will be produced. And another factor we can say temperature. If temperature is more, it will also increase the. If temperature is more, it will also increase the oxygen content. These are the very simple factors. If you go through this, you simply understand. You can understand. This is very easy. And another important factor I can say soil organic matter. Decomposition of the soil organic matter, the carbon dioxide is produced. So now these factors you just go through this. This is very simple. Okay. Another important factor is your texture. We draw the diagram. As we are drawing this graph, depth versus oxygen content. We already know that as we move from surface soil to subsurface soil, the oxygen content decreases. We'll see. Now consider as per the texture, we'll take three textural groups, and this is your clay soil, and this is your loamy, and this one is your sandy soil. So what happens here? We can see with depth the oxygen content is decreasing, and it is decreasing so much in case of clay soil compared to sandy soil. Why? Because of presence of microbes. Okay. Now we must see one of the important thing, that is your constituents. What are the constituents now in your soil layer as well as in the atmosphere layer? Okay. This is one of the important things we must need to know, so that we can compare how this aeration, exchange of gases, all these things happen. So we see actually the components that are in your atmosphere as well as in your soil layer, they don't change much. Okay, the components remain same, but the compositions change actually. If we see in case of atmosphere, this I think you all know. What is the nitrogen percentage? You can say 79%. Okay, I am writing it in terms of percentage. Okay, and your oxygen percentage is 21. Sometimes you write it actually exact value you can write 20.98. Rather, remember you can write 21%. But in your atmosphere, how much carbon dioxide is present? 0.04. Actually, in books it is written 0.03. Earlier it was 0.03. Now, actually, due to this climate change, we have already said the carbon dioxide concentration now increased. Okay. And in case of surface soil, we will compare the composition in both surface as well as subsurface soil. Surface and subsurface layer. So in surface layer, I can say the your nitrogen content almost 7.1%. Okay, and this becomes 20.63%. But the carbon dioxide concentration actually increases, we can say 10 times. Okay, that is we will write 0.25. In some books, you must know that it is written like that 0.03%, and here just normally 0.3%. This is the arbitrary value, but we must know the exact value. Now this is your class lecture type material, so we must know the exact value. But from the exam point of view, you can remember also that. Okay, and in case of your soft surface soil, I can say this oxygen content now decreases. We already see with depth the oxygen content decreases. This almost decreases to, you can say, 19.32. Okay, and your oxygen content is decreasing, then what will increase? Carbon dioxide. Okay, the carbon dioxide concentration may increase up to 1.48. Okay, this carbon dioxide concentration may increase up to 2 to 3% also. Okay, and here we can see the major function. This one is your carbon dioxide. Normally, the oxygen nitrogen concentration doesn't change much, but with depth, you can see the oxygen concentration is decreasing also, and carbon dioxide concentration increasing. So these are the main composition. Okay, and if now we know the soil composition, so next thing we will know how the movement happens. How this movement happens from one point to another. In case of soil water, we have also studied Darcy's law. Actually, remember always the Darcy's law. That will be applicable in soil air, soil temperature, everywhere. Analogous to that, we will develop the equations, but you must remember the Darcy's law. Okay? Now, if you see the movement of gases, you already know, I think, this is mainly governed by two processes. One is your mass flow, another one is your diffusion. And to understand this, we will take example of, let's consider here the partial pressure of nitrogen is your 2. Okay, partial pressure of oxygen is your 3, and partial pressure of carbon dioxide is 1. Okay, and in case of soil, I am considering these two. Okay, soil, just normally consider for an example. I am dictating this so that you can understand. In case of nitrogen, let it is 1, and in case of oxygen, it is your 2. Okay, and in case of your carbon dioxide, then there will be, it is 1 again. So what is the total pressure difference now? If you calculate total pressure difference, 3 to 1, 6, and here the total pressure difference is your 2, 1, 1. How much this is now? 4. So simply here we can observe how mass flow is happening and how diffusion is happening. You see the total pressure difference is here 6, and another pressure difference is here 4. We know the universal concept that energy always flows from higher potential to lower potential. Like this way, also your higher pressure air will move from high to low pressure area. This is very simple. So, in case of mass flow, to understand this mass flow, you must remember the gradient force is the main gradient is your total pressure difference. total pressure difference. I think from this example you must got this concept very well. Okay, so it is mainly happens due to total pressure difference, and in quantitative term we can write QV. This is your flux of air passing through mass flow, and this can be given by your minus small k by viscosity into your partial pressure, total pressure difference. This is, I have already told you, when this head drop like symbol is given, that means your three-dimensional unit. We are expressing this in a three-dimension. And what is K? K is your permittivity. Permittivity or permeability, you can say. Permeability. Permeability of what? Air. What is permeability? It allows your readiness to move the air from soil to from atmosphere to soil air. Permeability is very simple. It becomes permeable, so soil air can move. And this is your viscosity. The more the viscosity, the less will be mass flow. From this equation, you can simply know that with your increasing viscosity, the mass flow will be decreased. And your total pressure again. This is your total pressure differential gradient, you can say. Why this type of condition actually occur? There are many conditions. Because of convective flow, also because of this convective flow, this mass flow can also be regarded as convective flow. I am not going in detail about convective flow. I think this is very fundamental thing we all know. That is convection, conduction, radiation. All these things are very simple. And another factor which creates this total pressure difference, we can say temperature. If the temperature is high in the atmosphere, so what will happen? Now the pressure is decreased there. So air from with total pressure difference, the air will move from your surface soil to your atmosphere. Very simple. Another one is your pressure. We already talking about pressure. Temperature, to measure this temperature. We already we know in our very lower classes, Charles law is used to measure pressure. We use Boyle's law. Okay, this type of things I am not discussing. These are very fundamental things. Okay, and another factor which affect, we can say wind velocity. These are very fundamental things we all know. Okay, so here the question arises then: is mass flow is occurring in all soil depths? No, it normally occurs. Must remember, this mass flow actually occurs in surface soil because with depth actually the movement of you can now from here you can see the composition actually just changing, but the components are changed. So with total pressure difference in depth of the soil and moving to upper layer, upper atmosphere is very difficult. So normally this mass flow can happen in surface soil, and this much actually this mass flow movement of air is normally neglected. Almost 8 to 10% you can say aeration happens through this mass flow, or movement of air happens through this mass flow process. Now the most important process we will discuss, which you know, diffusion. So what is diffusion? We all know in all cases what is diffusion, from higher energy to lower energy simply, but in mass flow we are talking about total pressure. Here just remember, in diffusion we are talking about the gradient force. The gradient which will drive air from atmosphere to air atmosphere to soil air to atmosphere, like this way. This is a cycle. Okay, this way it can go, this way it can go. This is a cyclic process. The aeration happens. So here it is mainly due to partial pressure difference. Partial pressure difference. Okay, and you can observe from here. Now you see the partial pressure gradient of oxygen is 3 and here it is 2. So what will happen? From here to here movement will happen. From atmosphere to air, the aeration will happen. Very simple way. Although if you consider the total pressure difference now same for both. Okay. Now consider another example where the total pressure difference is same for your atmosphere as well as your soil air. But there is difference in composition of your partial pressure with one of the atoms like oxygen or carbon dioxide. Any one you can consider. If it is 3 and it is 2, for an example, so the movement will happen from atmosphere to soil air. If here we can say if the carbon dioxide concentration now partial pressure is same, no flow will happen. This is very simple, basic thing. Also to quantify this, we also in mass flow I have said that equation, and in case of your diffusion, all these are extent of your Darcy law. Okay. We have already discussed what is Darcy law. So this law actually given by Higgs. In case of soil air, the law actually which is given for movement of your air or gases, we can say given by Higgs. Just remember this type of things. And here we know the due to partial pressure difference it will happen. So the flux means quantity of air flowing per unit area per unit time. We already discussed like water. Flux always means that quantity or volume of water or air that is passing per unit area per unit time. Very simple. This will be now your directly proportional to what? Concentration gradient. Where the higher concentration will be there, it will move from higher concentration to lower concentration. This is very simple. And we already know in like Darcy's case, we will assign the constant value. Here I am assigning capital D. You already know why minus sign is given. So this is actually your Darcy law. This is flux. The unit will be your gram per centimeter square per minute. This is important. We will derive now. We will see how this flux is derived so that you can better remember. Okay, and this as in case of the Darcy law, we gave more important to hydraulic conductivity. Now here we can also give more example to this diffusion coefficient. Diffusion, this constant is called as diffusion coefficient. Okay, and no need to mention that this is the concentration gradient. Like your hydraulic gradient, here is gas concentration gradient. Concentration gradient. It's very simple. And this diffusion coefficient value actually varies from 0.6 to 0.8. You remember this value. Okay. This value normally ranges within 0.6 to 0.8. But we discussed about partial pressure difference. So, in terms of partial pressure, if you want to express, we know already ideal gas equation is your PV equals to nRT. We know, all of us know. Now, if P by RT, I am just taking RT from this side to this side, it will be N by B. This N by B is your concentration. We know, these are basic science. So, if you put the value here, your equation now becomes this I. Why is I is given? I is for any number of gas. For oxygen, if we take carbon dioxide, this is IL gas. This Qi now becomes minus D by dx and your P by RT. and we know RT value are constant, so we can rewrite the equation as your Qi now becomes minus d by RT dP by dx. We can write, and as this value is a constant, we can give it also another constant minus d dash, I say dP by dx. Now here we can see this again, the Fick's law now again is converted in terms of your partial pressure difference. Okay, this type of things you need to know. This type of, if you know this type of things, then your concept is very clear. Okay. Now we have talked about diffusion, flux. Okay, and diffusion coefficient. So how diffusion coefficient is affected? What are the factors now affecting? Like we have discussed in hydraulic conductivity also. What are the factors affecting? Here the diffusion coefficient. What are the factors affecting your diffusion coefficient? You know the movement of your air in water is very less as compared to in simple pore space. You know, in atmosphere the movement of your oxygen is higher in case of your gases as compared to water. It almost, with water the excess of oxygen decreases to almost 10,000 times. This diffusion, actually in water, diffusion of gases or oxygen rather increases. Diffusion of oxygen or flux is decreases with water almost 10,000 times. Okay, another thing you can say is what are the factors affecting diffusion coefficient. These are very simple. Still I am discussing one or two factors so that your idea will be very clear. Another thing we can say your temperature. If temperature increases, what will happen? The diffusion will be increased. The diffusion coefficient will increase. Here, as water content is higher, diffusion of oxygen is decreasing. Like 10 times, we can write D is diffusion coefficient is decreasing. Very simple. And another we have discussed already the texture, depth, all these things factors we discussed in your soil aeration. These are directly related to your diffusion coefficient. Now we know diffusion coefficient. Now we must discuss about this your flux. How this flux is calculated. We normally term this as ODR, oxygen diffusion rate. Oxygen diffusion rate. This is called as ODR. Or you already calculated, already know what is flux. So this is actually your flux. ODR or flux. This type of things are normally given. So this is our now interest in knowing how this ODR, oxygen diffusion rate, is calculated. So what is oxygen diffusion rate? The gram of oxygen diffusing across unit area per unit time. Very simple. Gram of oxygen diffusing per unit area per unit time. Very simple. Now, to measure this, we will take a ODR meter. We will take a ODR meter. This ODR meter. This is a ODR meter. Okay. If you now you see the instrumentation part. What is it actually made up of? How it works? We see. Normally there are two electrodes. What are they? One is your reference electrode. This is, I'll say, reference electrode. Reference electrode, which is made up of calomel, or we can say Ag silver, Ag chloride. This is soil surface. Okay, this is your soil surface. We are inserting this meter. So to this, another one connected electrode is your main, which will take the reading, is your platinum electrode. What is your platinum electrode? This is schematic diagram. Okay. This is your platinum electrode, where we can say this functions as cathode. So there should be, to give this current, we must connect also an anode. This is anode, which supplies actually the current. So the potential will be maintained. So what is the basic principle here? As this is your platinum electrode. This is your platinum electrode. In short form, I have one PT or platinum. Okay. So this platinum electrode actually here, this platinum electrode actually mimics, or we can say simulates your root respiration. Root respiration. What is root respiration? What is root respiration? This is simulates or mimics. You can write in standard terms. This platinum electrode actually, like where to aerate, to respire, as the root, your root take oxygen from soil air, it takes oxygen. Like that way, actually what we will do, we will maintain a constant voltage across the platinum electrode. We can say this platinum electrode is almost 4 millimeter size. You can say this size is very small, and 25 gauge instrument is used. This type of memory things we must remember. Okay, and the distance between these two electrodes, we can normally say 20 centimeter. And as we are discussing, what happens as this platinum electrode simulates your root, what will happen? Here a constant voltage is maintained because we are providing the current now provided. Okay, this will maintain a constant voltage of almost 0.55 to 0.75 volt. This much potential actually is maintained. So what will happen? I already told you this acts as a cathode. So what will happen? The oxygen that are in your soil, okay, they will be attracted and will be reduced to water. Okay, so for reduction of 1 mole of oxygen, we need 4 mole of electrons. Remember, this is the main thing to remember. To reduce 1 mole of your oxygen, 4 electron atoms are required. So here what happens? Like your root, it also takes your soil air and reduce it. So by this way, how much supplied oxygen will be there? That way we can calculate the ODR, oxygen diffusion rate for unit time. Okay. Now further quantify this. Actually, this process it will reduce the oxygen, but a time will come, then steady state will be observed. This is the principle. Okay, I am writing it step by step so that you can understand and also remember. So, there will be steady state will be observed. Oxygen diffusion rate will be reduced or steady state will be observed. So that actually occurs within 5 minutes. So this meter has a major advantage of we can analyze this ODR within almost 5 to 10 minutes. So this is the advantage of this instrument actually. So what happens now? As this steady state is observed, we have calculated, but we will use another law to quantify all these, which is we know Faraday's law. Use Faraday's law to understand this concept much better. Okay, he said what your current that is flowing is a product of A into small f, or you can say q, or I am writing f. Here also you in terms of q flux we are writing. Here you can write also f. Okay, small f. This actually this is the flux or ODI. This is actually the flux or ODI, which actually we are measuring. Okay, this is your current. This is your current, which is normally in amperes. Unit is your amperes. This N is your what? N is your number of electrons required to reduce 1 mole of oxygen. Very clear now. Here we have observed 4. So this N will be your 4. Okay. And what is F? F is your Faraday's constant. F is your Faraday's constant. And the value actually 96,500 coulombs per second. This is unit, or rather we can say value. And this A we know A is your area, surface area that we are talking about. It can be unit in centimeter square. So now from here, and normally this I actually expressed in terms of we can say microampere. I into 10 to the power minus 6. This way actually this total current is expressed to make our calculations easy. F. Sometimes you will face this type of equation, so don't get confused. This is simply your current in microampere. 1 ampere we know 10 to the power 1 ampere is we know 10 to the power minus 6 microampere. Okay. Now it is very simple. Now normally exams also ask what is the value of ODR value. From here you can calculate the ODR value. F is your flux or ODR value. F is your I into 10 to the power minus 6 by N F A. Okay, you put these values and you will get the information. So normally the range is your 20 to 30 into 10 to the power minus 8 gram per centimeter square per minute. Actually this is the range of your OD. And you must remember, for well aerated soil this value is actually between this 22 to 30 and your critical value is 20. If the ODR value reaches less than 20, then the plant starts to die. Okay, the oxygen supply will be very much reduced. Now you know ODR. Now we will see some parameters that way we can characterize. One parameter is your ODR. To characterize soil aeration, we will see what are the parameters we can use. What are the parameters used? Characterization of soil aeration. I will characterize now. One simple way I can say one is your ODR. First one we have already discussed. Second, to characterize this, we can take air filled porosity. Air filled porosity. This we have already calculated. How we calculate? Simply from total core, we will differentiate the volumetric particle. This is your total pore space, and in terms of water, we will say volumetric water. Just we will subtract, we will get the airfield porosity. Now, and also through apparent diffusion coefficient, apparent D, I can say. So what happens? We normally see the carbon dioxide concentration in soil air is high. So we normally what observe, oxygen concentration is going from soil air to atmosphere, and your carbon dioxide is coming from atmosphere to soil air. This is apparent diffusion coefficient. This is very simple. Another parameter we can use is your air permeability. Air permeability. What is air permeability? I have already told you. Permeability means the readiness or allowing the air to move through it. Okay. In field condition, if you want to measure, we will use air permeability. Air permeability. And in lab condition, we can also measure this using gasometer. These are the instruments you must remember. If someone is doing research in this area, he must have known, he or she must have known. Also, if you are in UG or PG, if you do research in this area, you also use this type of instruments. And another parameter, one most important parameter also, we can say your redox potential or redox parameters. We are quantifying the aeration capacity of soil. Another one important parameter by which we can characterize your soil aeration is your redox potential. We will discuss in detail about this in your soil chemistry. This potential actually is given in terms of pH. We measure this redox potential value in terms of pH. What happens? Some gases will be your oxidized state. Okay, this will be reduced, and from the redox potential value, we can say if the condition is oxidizing condition or reducing condition. From that we can say also from this value, pH value I will write down now. This value, if the oxygen concentration is higher or nitrogen concentration is higher, like that way we can characterize. Okay. If oxygen is in oxidized state, it remain as O2, and in reduced state it will become water. Okay. And we can say the redox potential value in terms of millivolt. I am writing. Okay, someone can write in terms of volt also. Don't get confused. P82, 320. Okay. And next one to get reduced is your nitrate. This will be reduced to your nitrogen. The potential value here will be 282, 220. Okay. Next one that will be get reduced, your ferric. Iron is present in oxidized state as ferric. It will be reduced to ferrous compound. Okay. Here the potential value will be your 282, 220. This actually this value are given by Patrick and Reddick in 1978. These values also change as given by your Dr. S.C. Doctor. Okay, in his book he also given this value little different. So I am telling as per the Patrick and Reddick paper. Okay. Now next one to get reduced is your sulfate, which will get reduced to sulfide. They here the potential now. Sorry. I have forgotten one important oxidation reduced state, which is your manganese. MnO₄ plus to MnO₂ plus. This is your manganese converting to manganese. Here we can say the potential now becomes is redox potential value is 180 to 150. What is redox? Simply the reduction and oxidation. Both are happening simultaneously. That's why it is redox potential. Now up to here the soil is in an oxidized condition. Okay, here fully oxidized, here partially oxidized, but it is in oxidized condition. Now the soil will enter to your reduced state. We will see the sulfate will reduce to sulfide. The potential value here will be minus 0.12 to minus 0.18. Okay, we can see the value are coming in minus because of reduced state. Last point to get reduced is your carbon dioxide. Carbon dioxide will get reduced to your methane. The potential value will be your 0.202 minus. I am writing it in terms of minus, negative value. Okay, this is your reduced state. From this calculation, someone can also characterize your soil aeration. Now we have characterized all these things. Now we move to what are the harmful effects of soil aeration. Okay, this, if the aeration is not proper, we know what are the harmful causes. Microorganic population will be decreased, flora and fauna will be affected, your organic matter decomposition will be lower. All these things you must go through your textbook. Very simple, just follow that, you will understand.